And then we'll go to the organometallics and catalysis. That is a new topic. And then the redox chemistry. Here we will learn little bit of what you have, little bit more than what you have already learned. The redox table you should have learned. Here we'll learn the diagrammatic representation of the redox data. And here, this material chemistry, we will not be learning. That is almost 1.5 lecture or 2 lecture that we will not be learning this semester. So you can follow here. This distribution may not go. Yes. This distribution of class may not go well here, right? Because we have only 10 classes. Okay. So we'll start from today from the bonding, and then we'll go to the coordination chemistry. And bonding will restrict to the homonuclear diatomic first row elements. And the heterodinuclear, I mean, only one we will study, that is a carbon monoxide. There's a reason for choosing carbon monoxide because we will be dealing this carbon monoxide in the bioinorganic chemistry. Okay. And then here what we have, here is the organometallic. Here also the organometallic chemistry. I hope you know the definition of organometallic chemistry. Here we will again limit to the fundamentals and the representative examples from homogeneous catalysis. There are 2 catalytic reactions we will be studying. There is a Wilkinson catalysis and then Monsanto acetic acid synthesis. And then we'll go, as I said, the redox chemistry. Here we'll talk about the diagrammatic representation. There are 2 diagrams that I will be teaching. That is the Latimer and Frost. Your tutorial teacher will briefly explain you about the Ellington diagram that you should have studied. You should have studied in during your class 12. In the coordination chemistry, one of the topic that I will not be covering, your tutorial teacher will be covering. That is the chelate effect, right? Chelate effect is an important topic. So this will be taught by your tutorial teachers. So please don't bunk the tutorial class, right? So they will solve, they give you problem and then solve based on chelate effect, thermodynamics, redox, as well as the organometallic chemistry, particularly counting the number of valence electron. So my request is that please do not bunk any of the lectures. That includes a theory here, what I teach, as well as your tutorial. Yeah, I have already mentioned. And how do we evaluate? This you should be familiar with by now because already 1 semester is over. Okay, but this time because of the limited the number of classes, we decided that not to put a lot of pressure on the students, though it is a continuous evaluation, right? That you make it clear. Either your theory as well or your lab class, it's a continuous evaluation. What I mean is that, yeah, you will be evaluated by assignment, a test before you go to your end sem or your, mid sem or your end sem. So there are 2 assignments. The last semester we had 3. This time we have reduced to 2 assignments. This assignment will be conducted by the tutorial teachers. Please listen very carefully. Your tutorial teacher will give you a clear instruction. This will be conducted. I will be posting the assignment sheet in the team, but you need to submit the answers according to the instruction given by your tutorial teacher, preferably in the Google form. They will share the Google form and then you need to upload there. We have only 2 assignments. Please do not bunk. Say, for example, what we'll be doing is that I am planning to take the 2 assignments. One is on 8th, another one is on 15th. 8th and 15th of May. Because we have the classes from today, and then you'll go, 26, 27, and 3 and 4. So you'll have a 6-hour lecture, and we can have it first assignment on 8th. And then another 3 class, 10 and 11, and then we'll have it the assignment on 15th. Because from 17th or 18th onwards, your mid-sem starts. So I don't want to interfere there. And then finally, you will have your final last class on 24th. And at the end of the semester, you will have the online test for the inorganic through Moodle platform. Okay, please note it. Your assignments will be taken on 8th and 15th of May. So this most probably a 1 hour or 1.5 hour, preferably 1 hour, and that will be conducted on Saturday. That is maybe in the evening hours, maybe 5 to 6. Or say the time we will convene.
Sir.
Okay, right. So here is a tutorial class details. So online platform is the tutorial teacher will be Google Meet. The link will be shared by the tutorial teachers, and these are the teachers. Your tutorial teachers' name and their email address. You can take a screenshot. Anyway, I will be sharing these slides after the class. Once I finish one topic, I will share, and then the video will be available in the team that you can download and you can communicate. Your tutorial teacher will send you a link to your institute email ID. Please follow the institute email ID. I repeat once again, please attend all the tutorial classes. Okay, let's go. Right, what we have is the inorganic chemistry. Right, you know that what is actually inorganic chemistry deals with. So basically, it deals with your properties and behavior of your inorganic compounds, which includes metals, minerals, organometallic compounds. So what we're going to learn from this inorganic chemistry, a lot of things are there to learn. So we will limit to the preliminary topics, the fundamentals, with a little bit of applications, so that you will be able to know why you are learning the inorganic chemistry. Say, for example, we should be familiar with this cisplatin, right? Cisplatin is used for, can anybody unmute and tell cisplatin is used for?
Cancer treatment.
Tumors.
Cancer treatment.
Cancer treatment.
Yeah, can you tell me once again, the speaker? Cancer, right? So the transplatin cannot work, but cisplatin works there. There's a configuration that matters. Okay, that is, we say that bind to DNA base in the cell and cause apoptosis of cancer cell. Right. So first one, what you're going to study about the chemical bonding. Right, you should be knowing what actually the chemical bonding talks about. We heard about, you should have studied the ionic bonding, or your covalent bonding, or metallic bonding. Let me go through here. Look at here. Can you see my screen?
Sir, can you show the previous?
Yes, sir.
Yes.
Yeah, previous slide. Previous slide up. What is that? Which one?
Sir, cisplatin.
Cisplatin. Okay. I think there is some delay is there. I do not know why.
Yes, sir. There is some delay.
There is some delay is there. Now I'm using a device. Okay. Now I think this will cause a problem. Okay. Can you see that now? Cisplatin.
Yes, sir.
Okay. I mean, we are not going to study cisplatin now, right? This is an example, right? So I mean, there is a delay. There is a delay. I don't know. Network is giving a trouble. Okay, so the chemical bonding, yeah. So you can see here, right? If it takes by this way, it will kill our time. So you can see here, I have given 3 pictures. That's all the 3 is basically a Coca-Cola bottle. So here you have your metal, yeah, the can, what you call it, made of a metal. Here what we have, here is a metal. Here what you have is the silica. But here you have your plastic, that is nothing but of your carbon. Okay. So all these, the function, all these, the basic application is carrying or holding the Coca-Cola, but the container is made up of 3 different materials. Here you have a metal bond. Here you have a silica, nothing but of your silica, and then here you have a purely of organic material, right? So what basically comes here, the unique is that One thing is that you have your three containers. One is a metal can, another one is the glass bottle, another one what you have the plastic bottle. One common thing that tethered together is the bonding. Okay, and again when you go further, I think it's a serious delay. Serious delay. If you open your computer, you will be able to see the see your the motherboard or the silicon chips. So what it is made up of actually basically made up of a semiconducting materials. Not all of them, some of them. The chips are made up of a semiconducting material. Again, that comes there, a bonding comes into picture. So though we will not be studying the semiconducting properties of the inorganic material. There is one example that comes there. It is a semiconductor that comes there in the practical application. Okay, right. So you can see here. What I will do is that let me check my network. There is some problem is there. Just a minute, please. I'm sorry for that. It's okay. There is a serious delay. Okay. Okay. So now you can see the board that is either in the computer or any electronic device. What actually basically what we have here is that your semiconducting material that is there. So basically what I want to say is that your bonding come into picture. Not only the bottle that you have seen, but also in the case of the electronic devices, that the material that is being used. When we go further, what we see that when you look at the biological system, say for example hemoglobin that we'll be studying maybe later. So in the coordination chemistry and the bioinorganic chemistry, either hemoglobin or the chlorophyll, or what we say is the vitamin B12, so cyanocobalamin. So there also what you have is the bonding comes into picture. Say for example, in the case of your oxygen binding at the metal center, in the sense when you inhale oxygen, the oxygen goes and binds. The oxygen transport mechanism. There again comes comes your bonding. So various aspects we have seen. Yeah, you can see the image here. That is what we have is the chlorophyll and your vitamin B12 and your hemoglobin. So now my question is very simple, right? How do atom combines, or why do atom forms bond? I give a typical simple example. Okay. Now I take a simple example. What I have on one hand, I have a sodium. Sodium is known for what is a notorious, right? It burns. It's a hazardous material. Another one what I have is the chlorine gas. So what do we have? You know the chlorine gas is used for what? Now these two are practically not usable. In the real sense, for practical applications, of course you use it for different purpose. This is a fire hazard. This is a toxic. Now I take the sodium and the chlorine gas combined together. What I have here is I get a sodium chloride. That's what we call the table salt. Right? Table salt, you have your table salt. Now, here you cannot do anything, but you have a beautiful table salt. Now everybody will agree that without the table salt, you cannot eat food. Right? How the bonding change the individual behavior, properties of the sodium and chlorine, and you get a material that is sodium chloride. That is how that is being used. What makes this unique? The bonding between your sodium and chlorine. We know that ionic bonding then comes into the picture. These two structures that you should have come across. right? What I'm going to talk here is that a bonding again is come into picture, right? Here, what you have, look at the NO2 and NO2 here, right? So here N is bonded to metal center cobalt, here oxygen is bonded to cobalt. Simply change in the bonding mode, whether nitrogen is bonding to cobalt or oxygen is bonding to cobalt, entire property of the complex changes. This is nothing but what you should have studied, that what we have is the isomerism, right? So if in the class 11 and 12 you should have studied the inorganic chemistry isomerism. There you should have come across the different type of isomerism. It's not only limited to that one. We have a hydrogen gas, sodium chloride that I have already mentioned, and fullerene, that the ball-like material C60, and your graphene, right? Recently, what we have seen is the graphene, right? With the wonder material, the pure carbon, nothing else is there. This is what the graphene. And then what we have a DNA, right? Now you understand that it's the coronavirus, that the sequencing genome. So in all that, one thing that is matters important is the subbonding. So you have your sodium chloride, here you have a C60, and you have your DNA structure. So one thing is very common. What is very common is the bonding. So nature of bonding controls the properties or the nature of the material that is generated. Now, number one, you see here. Number one, this is your ionic bonding. Ionic. Okay, this is typical example of what we sodium chloride. Already we gave the rock salt structure. Okay, and then on the other hand, you have your metal bonds. All your metal, copper, or your platinum, or your gold, whatever you have, you have an electron C. There you have your metal. So whatever, if it's a sodium, it's a sodium. In what we have an electron C, right? Now in between that, somebody comes into picture, is a covalent bonding, right? Say for example, you take your HCl or your ClBr, interhalogen compounds, or any other covalent compound, say for example HH or your Br. These are all covalent. We cannot say that 100% covalent. There is a percentage. I mean, predominantly, it's a covalent nature. When you study the bonding, you will understand that percentages may not be 100% covalent. There's a percentage of your ionic character. Maybe they're depending on the electronegativity of the particular element that is involved in, right? So now when we go back to the chemical bonding, when you have a quick look at, you can recall what you studied in your class 11 and 12. Right? What is the theory that you have studied for bonding? Can anyone unmute your microphone and tell me what is the bonding that you have studied?
VSCPR.
VSCPR. You said, I mean, you know, VSCPR does not tell anything about the bonding. It will tell about what it tells. Can anyone say?
Geometry.
Geometry, right? What is the shape or what is the geometry that comes into picture? Apart from that, you should have studied something else. Anything else?
Hybridization.
Hybridization. Right. Hybridization comes under what? This is a delay is killing our time. Right. Okay. Now look at here. Now what we have? A valence bond theory. Simply say that VBT. Okay. So the bond formation, according to Pauling, right, is received the Nobel Prize twice, right? 1954 and 1962. Okay, let's not go to that. We don't have much time for that. Okay, so Linus Pauling is known for the valence bond theory, and then whenever we talk about, somebody say the hybridization. Immediately we'll say the hybridization. Typically, you should have studied your D2sp3. Say, for example, this complex, chromium, the hexamine complex. You have a D2sp3, and you will, I mean, play around with the orbitals. Now, what it says is that simply a overlap between, yeah, say, for example, S and P orbital or D orbital. As a result, you get a hybridized orbital. At the end of the day, you will be able to explain to some extent, the bonding in the sum of the complex, the compounds or the complex. But one thing is important to know that the valence bond theory cannot explain the bonding in inorganic complexes. I mean, valence bond theory is a god for organic compounds. You can comfortably explain the bonding in organic compounds with a valence bond theory. Use a hybridization, sp3, sp3d2, or d2sp3, whatever that you put it there, you will be able to explain. But on the other hand, you will never be able to explain the bonding in inorganic complex comfortably. I'm not telling that we cannot do that, but convincingly you will not be able to explain with the valence bond theory. What we need to bring it here is another two people came, Mullik and Hurt, that you should have heard about it. Again, we are not going for the history of that one. This is talk about the MOT. MO theory, right? I mean, in the class 12, I suppose that it is there. So what we have, a hybrid. Again, we are talking about the overlap, right? We don't call it as a hybridization. What we call it is an overlap. Say S orbital here, and here is a P orbital, right? If there is a effective overlap, there is a bond formation. If you draw the diagram by this way, say for example, your potential energy versus the internuclear distance, how do I do that? I bring two hydrogen atoms to close to each other. Say for example, here I have a 2, and then bringing close internuclear distance, interatomic distance, I bring it close. Now at one stage, it started overlapping with each other. Say for example, the s orbital is there in the hydrogen atom, it starts to overlap. Some overlap, some attraction that is taking place. Now, at one point of time, I'm following the potential energy, right? At one point, a minimum, what we call the potential well, right? A minimum energy is coming, and then again you force these two atoms beyond a particular distance. What I mean in the case of your hydrogen, if it is beyond 74 picometer, your energy start increasing because there is a limit. Then after that, you have an internuclear repulsion, right? As a result, the energy increases. Significant overlap.
One doubt. So, in case of like this is a potential energy internuclear distance graph. So, sir, if we take the derivative at any point, won't it give the magnitude of the like restoring force? So, at the point of the minima, won't the force be zero? So, how can we say maximum attraction?
No, what is it? How can we say?
So I was saying ki if we take the derivative of at any point, will we not get the like the force here?
No, I did not get your point, right? What we do is that let me finish that, and then I will get back to you.
Sir,
Right?
like force can be defined as minus of del U
Yeah,
by del R.
I do understand. I do understand. I'm not going to give you any mathematical treatment now because we had mathematical treatment last semester and the earlier year. Now we will not be able to bring the force and then write an equation. All this I will not be able to explain. These are all very fundamental. Again, we are ready to go to the actual syllabus. Please be patient. I will explain you later. Okay, right. So I mean, this is what I'm doing is that I'm hypothetically, I mean, bringing two atoms and then I'm drawing this to the potential energy diagram. At one point of time, what we have, I have a minimum energy. Say, for example, these are all proved, right? I will explain you at the end of the bonding how it is. Say, for example, minus 436 kilojoule. What I have is the bond strength. And beyond that, what happens? The energy of the system increases simply because we have a repulsion. What is the repulsion that we have? Is there's a internuclear repulsion that comes there. You will not be able to see a bond between H and H. Beyond this distance, the energy goes beyond, and you will not be able to see this kind of a bonding. Okay. Right. Now look at here. Now what we have, I have already briefly mentioned. Now what are the limitations? Briefly I mentioned in the valence bond theory. What are the limitations that we have? According to valence bond theory, the electrons should be localized because we said that hybridization, in principle, if VBT is true, all the bonds, all should be, it should be localized. But we know that there are plenty of molecules. We have a delocalization of electrons. That is, that cannot be explained with your valence bonding. Bonding in complex, as I mentioned there, you will not be able to explain convincingly. You can explain. We said that, sir, we learned the chromium hexamen complex, D2sp3 or sp2, we can explain, but the associated property cannot be explained simply with the valence bond theory. For example, number one, it cannot count for the colors of the complex. Valence bond theory, you will not be able to explain the color of the inorganic complex. Again, don't make mistake. This is purely, I'm talking in terms of inorganic chemistry. Valence bond theory is well and good to explain the bonding in organic molecules, not in the case of inorganic complexes. May predict, we will see that, may predict the magnetism very wrongly. The actual property may be diamagnetic, but the valence bond theory will be this, that is paramagnetic. More importantly, you should have studied about the spectrochemical series. You cannot explain your spectrochemical series with the valence bond theory. So now here comes the molecular orbital theory. What actually molecular orbital theory? This is a big topic. Basically, this is a quantum mechanical treatment. You may love to study, but we don't have a time to study the mathematical treatment. So we will directly go to the MO diagram, and then I will explain how we interpret the properties using the MO diagrams. Okay. Basically, MO theory is based on the quantum mechanical principle, simply based on the linear combination of atomic orbitals. Okay, now I put here. Okay, quickly read through it, then I'll explain this. What we have here is the electron in a molecule or in an atom. What you are going to say that you are defined by a wave function psi. That's a fundamental treatment. Again, we will not be doing the quantum mechanical calculation. So what we'll have is that each psi is associated with a definite energy value, and you will have the electron. That electron should have a spin with a plus or minus of what we call the spin quantum number, ms. And then what we need to do is that we need to fill up the electrons in the MO diagram according to the two principles, right? What we have a principle and then Pauli exclusion principle, what we say, right? These two are. Very important thing is that this you keep in mind. This is where this psi, the wave function, all this we are not going to study. This is beyond your syllabus. This you remember. What I mean, this is the linear combination of atomic orbitals. So what I actually mean by linear combination of atomic orbitals? Read through is basically what we have, linear combination. Let me explain you. There are two things that you need to understand. Say, for example, you have a, imagine that you have two balls, right? Consider that these two are the hydrogen atoms. You are bringing close to them, close to each other, as I have shown in the potential energy diagram. Okay. Now you're bringing close to here. The atomic orbitals of hydrogen can undergo overlap. The overlap is basically depends on, there are two things. Number one, the symmetry. What we call the symmetry. Number two, what we have is that, what we have is the energy. Energy. What I'm talking about the energy? Each and every orbital has their own energy. So two things that we need to remember, that is what we have. So the symmetry, another one is the energy. Both should be similar. I'm not going to tell that same, should be similar. If the balls that I have in two hands, if both of them have a similar symmetry and similar energy, if I am bringing close to each other, is to explain you. These two are coming close in contact, can have an effective overlap. Okay. So I hope you understand. There are two things that we need to understand. That is, the one is the symmetry, another one is your energy. These two are the major player in the MO theory. When we talk about the mathematical treatment in terms of quantum mechanical treatment, we'll talk about the sign. Right. Again, we are not going to study. Look at this diagram.
Excuse me, sir.
Yes.
Sir, why the energy similar are required? I didn't understand.
Yeah, I will show that. I will show. Right. You please be patient. When I show the molecular orbital diagram, so you will be able to understand here. But from here also you can understand. Right. Say for example, you look at here. This is one of my atom. Right. This is another atom. Right. What I have designed as a psi A and psi B. Okay. This you consider as a hydrogen or any of that. Right. Let us say A and B. You have A and B. Now what we have here is we are talking about the linear combination, LCAO, linear combination of atomic orbitals. Okay, so the primary condition for the linear combination of atomic orbital is what? Number one is your symmetry. Number two is your energy. Somebody asked the question, why, sir, that the energy should be similar? I'm not going to say. Say for example, let me draw. Right. Say for example, I hope you will. This is your A, and another one is there B, which is energy somewhere here. Right. This is the atomic orbital of what atom A. This is the atomic orbital of another one. Let us assume that it has the same symmetry, say spherical symmetry, say S orbital. Now the energy gap between these two are, say for example, more than 500 kilojoule. So on what basis these two will come and close to have an effective overlap? There is no question of overlap. So what should be there? The energy should be similar. I'm not telling the same. Here what is shown is the same. Right? This and this have the same energy. But it is not necessary to have the same, a similar energy. Right? But let me explain you. There are three things whenever we talk about the linear combination of atomic orbital. So look at here. Number one is that there are three integral comes there, right? Don't much bother about it one. I need to tell that. Though I'm not teaching the quantum mechanical treatment, these three terms are important. So that the question will not be coming from the integrals because we are not teaching. But in order to explain this MO, I need to bring these three integral. One is a Coulomb integral, that's a ground state energy. What I'm talking about, the E. Another one is a resonance integral. That is what I'm talking about, the beta. That is the measure of the strength of the bonding interaction. Right. The third one is the overlap integral. The extent of overlap. Right. I will show the extent of overlap maybe in the coming slides, either today or the next class. Number one is the ground state energy of that particular atom and the molecule and its. And then resonance integral, to which it undergo, I mean, the bonding strength is how it is overlap, to what extent, that is decided by the overlap integral. Okay, so there are three things. Number one, what we have here is a ground state energy, and the second one is your extent of the bond strength and the extent of your
Excuse me, sir.
Yeah, can you ask this question at the end? So that will be easy for me. So
Okay,
that
sir.
I will be able to explain it. Okay. Now, so when two atomic orbital mix, you get a two molecular orbitals. Okay. Each orbital can have a two electrons. That's what we know. I think we don't need to explain further. And then also we know follow the alpha principle. This already know. Hund's rule, that also you know. Then this is also very familiar. You already studied in your JEE. That is bond order. I will give you example. Don't say that sir has not explained this. Bond order is bonding electrons minus antibody electron divided by 2. Right. This is, I hope you should be very familiar with this one. Again, I will bring some specific example. At that time, I will ask you to calculate. Okay. So two atomic orbitals, you get a 2 MO that you keep in mind. And then the Pauli exclusion principle, alpha principle, and Hund's rule. So that you need to remember. Okay. Now look at here. Again, don't bother about this mathematical given wave function that I have given. just to represent. We are not going to study the depth of the quantum mechanical treatment of MO theory. Okay, so linear combination. What we have here, I have a psi A and psi B corresponding to one atom, another atom. If it undergo an effective overlap, if I represent this MO, psi A, n is the normalization constant. Again, we will not be able to go into the details. There is a lot of slides are there. So this time I am not explaining. So it goes here is simply, right? This is your overlap integral. This is the probability density. What I mean with probability density, now you will say the sir is bringing so many terms, I do not even understand. Right? I want to explain only the overlap. I'm not going to ask anything about the probability density or overlap integral or resonance integral or Coulomb integral. These are the fundamental of from the mathematical treatment. That's what we call the quantum mechanical treatment.
Sir, we have studied somewhat quantum mechanics in first semester also, so we understand sometimes.
Okay, okay. So then I don't need. I hope you already studied physics, right?
Yes, sir. In physics of waves, we had quantum mechanics.
Okay. Anyway, we are not this semester. I'm not going to teach about any quantum mechanics. I will simply go to the MO diagram. Okay. So, but I want to say that this is the MO diagram doesn't come. I mean, falling from heaven. There is a rational, mathematical proof to show that there is a bonding and antibonding orbitals are there. Okay. Right. Now look at here. Now what happened? Again, it's a pictorial representation. Now you have your orbital 1 and orbital 2. We define in terms of a coefficients which is equal to 1 because both are from same origin. Say for example A and A, right? If it is A and B, you may have a different the value for coefficient. And then you have your bonding. Yeah, this one, what we say that psi G. The gerade. This I will explain you after a couple of slides. If time permits, after a couple of slides, I will draw and show you how do I call that a gerade, right? Now what we have, the wave reinforce. Again, this is basically a quantum pictorial representation how two waves reinforce and you are getting here. These are the nuclei here. And then two waves reinforce. There are conditions. What are the conditions? For the waves to reinforce, number one, it should have a similar symmetry, and number two, a similar energy. If these two are not there, we cannot talk anything about the reinforcement of the wave, right? Now what we have, yeah, this is another pictorial representation. Your Atkins textbook will go here. This is a funny picture, right? What we have, there are two people, two atoms, yeah, come together. Right now they are sharing the single eye. I hope you understand. Right? This is to make you understand how the bonding come into picture. Now these two are inseparable due to the wave reinforcement or effective overlap between the two atomic orbital, what we call the linear combination of atomic orbitals. Another way of representing, right? What we have, I think we'll skip. Again, the same thing I'm repeating. Now, what we see here? Now, basically, if you go here, now what we got here is that here what I got a bonding MO. That's to keep in mind. Your bonding MO. So where we reinforce, resultant is the bonding MO. Just opposite, what we have, if the waves are not reinforcing, if the waves cancel each other, what happens? You have a nodal plane here. What we say is an anti-bonding orbital. Okay. Now what we have? I have an overlap between two atomic orbitals. One results in a bonding MO. Another one is result in the anti-bonding MO. Because whenever I have a two atomic orbitals or I have a n atomic orbitals, I will be getting n molecular orbitals as I have shown there. Now what we have a destructive interference. I hope you got it what I mean by destructive interference. N nodal plane is there, right? Nodal plane perpendicular. The energy of the electron in this orbital is higher. Now you can see here it is cancel each other. Then mathematically we represent here. Okay. Again, what we have, the electron is excluded from the internuclear region. Yeah, basically what we say is that destabilizing. Now I put here as a diagram. Okay. Now here I have, this is one of my atomic orbital. That is your one side. Another one side, what I have here is another atomic orbital. Now assume that it undergo an effective overlap and you are getting a bonding, and here you're getting a antibonding. Now, I mean, some of you may have a several questions now, sir, how do you tell that there's a bonding and antibonding MO is there, right? Yeah, now it's very difficult for me to explain you with this diagram. For that only, what we'll do is that we should derive the quantum mechanical treatment using variation theorem. I am not sure how many of you have heard about the variation theorem, but the variation theorem, and then we derive and we show that yes, bonding as well as antibonding MOs are there. Okay, now you can represent by this way and you can represent by this way. Not much to explain here. It is a diagrammatic representation. Basically, again, what you need to understand that the linear combination of atomic orbitals. Again, going to the potential well, right? Potential well, I have already explained. I will skip this one here, right? I will skip here. I will go to this one. Okay. Yeah, I think it is. Look at here. So what I have taken is a typical example of hydrogen molecule. Okay. Now I have a hydrogen atom, A and B. It's a homonuclear diatomic, right? This is H2 in the subscript. Okay. Now what we have done is that what I have done, yeah, this is undergo a overlap, and then you get a bonding and an anti-bonding MOs. Now again, some of you will get, sir, how do you say that? How do you prove that this is a bonding and anti-bonding MO is there? Is it really there? Yes, it is there. Now you can represent here you are bonding the reinforcement of the waves. And here you cancel each other. Here you have no electron density, but you have a maximum electron density is here. Now what we have, so how do I prove? Now you may have a lot of questions. Sir, really it is there? Yeah, we can prove that there is a bonding and anti-bonding MOs are there, right? Now, this is the energy gap between your two MOs. What are MO I'm talking about? A bonding MO and an anti-bonding MO I'm talking. What is that? It is 11.4 electron volt corresponding to a 109 nanometer. The location of the bonding orbital, there is a dissociation energy is equal to 4.5 electron volt. This is not theoretically, it is experimentally observed values. Again, I will, at the end of the bonding, I will tell you that what is the experimental technique that we can use to know, is it really a bonding and anti-bonding MOs there? Yes, it is there. We'll be able to get a signature corresponding to each electron. If I have one electron here, and then say for example, one electron is there, and this electron can be understood by measuring what we call the photoelectron spectroscopy. I will explain you briefly at the end. So now I could qualitatively convince you that whenever there is a overlap between your two atomic orbital, according to the linear combination of atomic orbital principle, then there is a MO as well as a bonding MO as well as anti-bonding MO. Right? Now I will skip this. You'll go here. Now look at here. Okay. So now I've simplified everything here. Now I have given. I hope you can see the quality of the image is maybe not very good, but let me zoom it a little bit off, and then I will be able to show it here. Right. So here, what I have shown here is this side, right? This side, my left-hand side, and my right-hand side. So here, what I have given is that yes, a greater than 0. What I'm talking about this is one of the integral that I have mentioned. That's an overlap integral. What is the meaning of that? What we say is that the extent to which these two atomic orbitals, say for example A and A, at what extent they overlap. The extent of overlap that is decided by the overlap integral. If it is greater than 0, what we have is your bonding. And if it is less than 0, this is your anti-bonding. Okay, now you will have these are in third category. Now this is the first category, and this is the second category, and the third category is there. What we have, right? What we have is that the third category you have your non-bonding S equal to 0. What does it mean S equal to 0? Can anybody say that? I'm talking about the non-bonding. From the diagram, can you explain? I will little zoom it.
Sir, there is no effective overlap.
There is no effective overlap at all. Why there is no effective overlap? Why there is no effective overlap? Can anyone tell?
Sir, first is due to geometry.
Orientation is not adequate.
This energy may be similar, but the symmetry is not matching at all. Say, for example, you see, you have your p orbital and an s orbital. How it comes? If this s orbital, say for example, if this s orbital comes in this direction, it can undergo effective overlap. Now this is coming here in this direction. There is no effective overlap. S equal to 0. Then these electrons in this orbital would be called the non-bonding electron. There is no effective overlap at all. I hope you got it. Here you have a symmetry and energy matches. And here, if a bonding is there, anti-bonding should be there, right? Don't think that, oh, bonding and anti-bonding is different, right? I hope you got it, right? Now, again, little bit of, right? I mean, look at this diagram, right? Don't look at the mathematical equation, right? So now look at here, right? Again, I'm talking about the bonding and anti-bonding, bonding and anti-bonding. In the case of your p orbitals, okay? So if there is an effective overlap, and then you have your MO, is basically based on the calculation, computational calculation. You get your diagram of this. Here, this symmetry and this symmetry does not match here. You are not getting here. You are getting an anti-bonding. And again, it goes again the same thing. I'm repeating. I hope I don't need to explain here. The same thing is a lateral overlap. So lateral overlap results in what? What do you get? What is the bonding you get?
Pi.
Pi bonding. Right. Very good. Right. And again, it does not undergo. Okay. Right. This here I have summarized everything based on the p orbital. You have your pi effective overlapping, and here you have a pi bonding, and here is anti-bonding, and here also. Here, one thing you need to remember, we'll come back. I mean, we'll see that this is very important, right? What we sigma g, I have not explained, and then sigma u. Sorry. Okay, sigma u. These are the two symmetry we'll be talking. Maybe after a couple of slides, I will explain. The same way, pi u, and then basically gerate and ungerate. Okay, right. Again, this is a quantum mechanical treatment. Let us not forget about it. My goodness. Okay. Look at here, right? This is very important, right? So what is very important? Whatever we have already learned, that you have effective overlap and you generate your MOs. Now you have a Pauli exclusion principle, alpha principle, and Hund's rule. All these are there. Now one should know, right? You can read that one. One should know how to write the MO electronic configuration. This is very important, right? MO electronic configuration. This is important. How do I know? How do I write a MO electronic configuration? First, I need to know how the MO is built up. Basically, what we have, say 1s orbital and 2s orbital and 2p orbital, say for example. So if I'm taking A and A, the 1s of A and 1s of A will overlap. You get your MOs corresponding. In the same way, 2s orbital. You generate, if it is a 2s, again your 2 MOs. In the same way, the 2p orbitals. Now, we need to build up the MO diagram, MO, according to the energy, and then fill up the electrons according to the alpha principle, Pauli exclusion principle, or Hund's rule. That's what we have already studied. You fill up the electron. Once I fill up the electron, what I will know, I can calculate the bond order. Then I will be able to say that whether this molecule really exists or doesn't exist. So note it down here. Sigma 1s star, sigma 2s star, 2p, I mean pi y, pi z, and then pi y, pi z. So I will show the diagram and explain you little later on. Right? We have another 4 minutes, and then I will leave time for me a couple of minutes. So look at here. The orbitals, the molecular orbitals or the atomic orbitals can be classified in a different way. So one way is that, again it is slow. Okay. Okay, now you can see here, right? Now this one, 2s orbital undergo overlap, you get your sigma. This again you already studied in the class 12, right? Here S and P undergo overlap, again you get a sigma orbital, and then P and P, right? This is an example, right? In the same way, what we have, pi orbitals. And then little bothering maybe, you may be puzzled to see that delta orbital. Yeah, there is one example. Again, it is not there in our syllabus. What we have is the bimetallic clusters. There you will have your delta orbitals. Right? You will not be studying all this one. Just to make you to understand that there are delta orbitals also there in rarely most of the metal clusters, organometallic or other inorganic clusters. Okay, I will finish with this one. Right now, I'm going to talk about the gerate. Okay, this is I'm talking about the orbital gerate. Okay, now I'm not going to talk about the MO symmetry. I'm talking about the orbital symmetry. Right, this is basically what we have a s orbital. How do I know that this is gerate or ungerate? Right, what you need to look at here is that you need to look for a way, right? Let me go. I think it's not okay. Now look again. It is the time delay is, my goodness. Okay, just a minute. Critically, this much delay it is giving. Yeah, you can look at here, right? I am drawing here. So the center of inversion. You can look at the center of inversion at the center. Right at the center, I start from here and go here. Okay, I start from A, I go to B. Through the center of inversion, center of the orbital or the molecule or whatever it may be. If I end up with the same identical position, identical one, now then I call this as a gerade. What is that gerade? It's a symmetry. Okay, quite straightforward. Now I look at the p orbital. I start here. I have a center. It's not the center of inversion. Here I say the center of inversion, but here I call the center. Now I start from the top, the purple one, and pass through the center. I am ending up. Here is my A position and B position. Both are not same, not identical. So if that is the case, I give the notation as U. That's an ungerade. Here I have given gerade. Here I have given ungerade. Now I talk about the d orbital. I move from here to here through the center. I have a position and B position. Then what I have is that I end up in there. What I get an identical. Then what we say this I call is gerade, right? Okay, I think I don't want to keep you more. Already 105. I will finish up with this one. And then next time, next class, tomorrow when I come there, I will start with a molecular orbital symmetry. Very similar way, right? Very similar way. What you can see here. Very similar way. How do we assign the assign the symmetry? Let me take my attendance and then let me stop the recording. And then now what you do is